Thank you very much. It's very exciting to learn some of this material with you. I'd like to talk about joint work with Jesse Kass, Marc Levine, and Jake Solomon. Time permitting, I'll talk about some computational work, joint in progress with Erwan Brugallé, but let's communicate. Riome already introduced the A1-homotopy theory of Morel and Vygotsky. In greater context, and I very much enjoyed your lovely talks, except for your notation, but we'll copy it in any way. We have P for sheaves, for Nisnevich sheaves that are A1 invariant. On smooth schemes over a base scheme S, and this makes a homotopy theory inside pre-sheaves, which are functors from the opposite category of smooth schemes over S to simplicial sets. And let's call this H of S. And then we've also seen the P1 spectra for this V. Which is our stable A1 homotopy theory. And a beautiful theorem that Cheol sort of brought up in the last talk is that Morel computes the endomorphisms of the unit in this category. So the 1, in SH of K for K a field is a computable group. It's not quite finitely generated, well, it's not finitely generated, but it's there's for many interesting fields, including number fields and local fields, there's a terminating algorithm for writing things down. So computers compute with this. And it's important for this talk that this is a computable group. So let's talk about it. This is the Grothendieck-Witt group, having nothing to do with Gromov Witten. It's just the same letters. And it's defined to be the group completion of isomorphism classes of symmetric, non-degenerate, bilinear forms over K. And it has a presentation. Any form, any non-degenerate bilinear form can be diagonalized with generators. The one-dimensional bilinear forms, so a bilinear form on the vector space K, it sends xy to axy. For it to be non-degenerate, we need a naught to be 0. And then it has relations, which says that if we change the vector space basis by multiplying by b, we get that b squared a is a for a and b in K star. And a little linear algebra can teach us that the diagonal form with a and b on the diagonal has a new basis like this. And it's computable in the sense that if you're a tall dimension was finite, there's a finite sequence of invariants that you can apply to some list of numbers and brackets. So our group will contain numbers and brackets. And our calculations will look like that, but we can tell when two are the same by applying a list of invariants of quadratic forms which are the same as bilinear forms and characteristic not two, which come from the Milnor conjectures. So the first two will give us, here's some examples. The Grothendieck-Witt group of a finite field, FQ, we can take the dimension of the underlying vector space V. So and this is the rank, which sends that bilinear form over there, sends V cross V to K. It goes to the dimension of V cross the discriminant, which sends it, this same bilinear form to the determinant of, let's call this beta, of some basis Bi, Ej. And so this is well defined up to squares, because if you change their basis, you'll change this by a square. And so you get the Grothendieck-Witt group as a group is isomorphic to the dimensions FQ star over FQ star squared. Another good example is that if we didn't have any two numbers A that can't be made one equal to the other by multiplying by a square, then all of our generators are equal. So we get that the rank map gives an isomorphism with Z, and the Grothendieck-Witt group of R, we have two kinds of elements of K star over K star squared, 1 and -1. And if you take the difference of the number of ones and the number of minus ones, this is the signature. And up to a parity, up to the fact that they have to have the same parity, this is an isomorphism to Z cross C. So we're working in a computable group. Let's compute the degree. So it has a property that if we worked inside R, that we could pick up both the degree of the real points and the degree of the complex points. So we have the degree down to GW of R, and if we take the rank of our degree, we'll get the degree of the C points. So in normal topology, but this is taking the C points. So a P1 goes to an S2. And we could also take the R points and look at maps from spheres to spheres in topology and take the degree. And we've combined the degree over C and the degree over R. So how to compute the degree? It's a count of the points in a fiber, and it depends how the map is given to you. But for instance, we've seen that P1 wedge n is Pn over Pn minus 1. And if you had a map from Pn to itself that was finite and sent Pn minus 1 to itself, so we have a map that's given by some f from Pn to Pn finite. So the degree of such a map, between spheres is the sum over a fiber of a weight. So for an appropriately picked point of the bottom for some y, a k point in Pn, we can look at all of the elements of its fiber. What Lan and Morel tell us to do with the points in the fiber is they say, let's remember something about the field of definition of this point. And here it is. We'll define it in a second. Well, let's assume that y is a k point. Then they say that we'll put in brackets the derivative, how fast the function is changing. So the determinant, or the Jacobian determinant, if we put coordinates on the AN, and we've got AN mapping to AN by assumption. So here, this piece that's picking up the field of definition of the point of the fiber is defined. So if let's say that F is a tall on the fiber, so that we can put that determinant in brackets and it's not 0, and that we also have a separable extension. So then a separable extension of fields, k to k of x. So if we have a separable extension, what we do to record the fields is a map trace GW of L to GW of K, which pushes forward the form on L. So to V just viewed as a vector space on K, and then the trace from Galois theory. So recently, Thomas Brazelton, who's here, and Stephen McKean and Sabrina Pauli have a beautiful classical formula in terms of Bezoutians that they show is the same as the A1 degree. And we have some kind of count of points of fibers of a map.
So there are local coordinates on the fine charts, but when you change to another chart, you change the coordinate, you change the Jacobian by something which is not a square.
Yeah, so we have to orient the map, but when the map is from something to itself that is oriented, we're just going to use the standard ones on AN. So in general, when we take the degree of a map, we're gonna orient the map first to know, so that we know which coordinates are compatible with the given orientation. So I claim that we don't have to do that here because we have a standard choice on AN, but that's a great complaint. And in general, when we take degrees of maps, let's fix some extra data. And then there will be a data of an orientation of a map. And then when you want to take a sum over the fiber of various derivatives, you have to take those derivatives with respect to coordinates compatible with the orientation. So, thanks. So just take the standard ones on AN. And we're actually going to talk about it, so. GW of K is the global sections of a sheaf of pi 1. So for X and our homotopy theory, we're going to define pi naught of X as the Nisnevich sheaf associated to the pre-sheaf, which sends a smooth scheme U to homotopy classes of maps in H from U to X. And if we want to do the stable version, and we'll do then we've got a point here. What we have is that pi naught, or what Morel has, is that pi naught of the sphere spectrum is a sheaf version of GW of this, and we're going to make it a sheaf just of rings, or let's say sets, and it's the Nisnevich sheaf associated to U mapping to the group completion of symmetric non-degenerate forms on vector bundles over U. V cross V to O of U vector bundle. And GW underline is known to have the following lovely property. It's unramified. In the sense that if we have a section that's over a big open, it extends to the whole thing. So if you have U in X in smooth K with the codimension of the complement at least 2, then the restriction map is an isomorphism, and you can, and there's another property of being unramified by being picked out by certain valuations. So if we'd like something on GW of X, we just need it on a large enough open. Moreover, it's A1 invariant. So it'll pass through, it's an A1 invariant sheaf of sets, so it will really pass through pi naught. So there's a canonical map for if we've got something in our A1 homotopy theory, we got a canonical map from X to its pi naught, and then GW of X is the same as GW of pi naught. So then GW of pi naught of X is the same as GW of X. And let's view that as a sheaf. So we'll view that back in HK, and so we'll view GW of pi naught of X as there's the maps of pre-sheaves. So these are still sets.
Where is pi naught X?
Let's say pi naught and H of K.
In this.
Yeah. But it's not a space of GW. There are lovely spaces of GW, but we're going to compute things in a discrete way. Let's do some degrees of maps not between spheres. Let's give enough data to compatibly take derivatives. So F is oriented, a map between X and Y is oriented by the data of L on X, a line bundle, and an isomorphism let's take X to be a local complete intersection morphism. So we have a line bundle, which is the determinant of the cotangent complex, and which has, so this Serre duality is holding with this great line bundle omega f, so the Jacobian lives in here. If you were something smooth, the Jacobian is naturally a section of this. So if you want to know what the value of the Jacobian is, you have to choose a trivialization of this, and then up to squares it's well defined. Or it's just a push forward in Hermitian K-theory if you want to define a degree. So let's give ourselves an orientation at least over a codimension 2, a complement codimension 2 open. So U open codimension of y minus u greater than or equal to 2. And then we just restrict to the inverse image of u. Let's call this G. For simplicity with push forwards, just to make them still vector bundles, let's assume this is finite flat, and then define the degree. The degree of f in GW of pi naught of y is the class of the form that we'll get on O of u by pushing forward L. And then, so we've got some vector bundle here on u, and then the orientation allows us to identify G lower star of L squared with G lower star of the canonical sheaf. And I forgot to say that this is finite flat and oriented, and our degree will depend on the chosen orientation. And then we have the trace from Serre duality, which we've seen before in this is the compatible with the trace from GW with the K and the L going to O of u. So then degree, it's the class of this form. Okay. So under certain circumstances, we have a degree in.
So you at least you have to assume Gorenstein, or you say local.
Actually, that's even weaker. So you're saying we don't have to assume LCI, we could do Gorenstein.
Okay.
That would be fine.
Just for this, you still need to have a line bundle. So.
That's it, yeah. But LCI implies Gorenstein. So you could make a stronger definition. So we make a bunch of different constructions of degrees under different hypotheses in this preprint. Actually, Gorenstein isn't one of them, though. So we've got this degree in pi naught of y. Pi naught of y is k when y is A1 connected by definition. So pi naught of y has a natural map to the point, just like everything else. And if this is an isomorphism, it's A1 connected. And then so, which implies under the above hypothesis that the degree of f is in fact in GW of k. So for example, if y is covered by affines or has an affine stratification, it's A1 connected. So these are examples of A1 connected smooth schemes. So y with an affine stratification are covered by affines. if we have a smooth proper surface over a perfect field, it's a result of Ashok and Morel. So Y smooth proper surface over a perfect field. Which is K-rational. Sorry, that's too much to hope for. So being A1 connected means that your R points and your C points are connected. So we can see right off the bat from our favorite examples of real surfaces with more than one connected component that we. So what we mean is K-rational, smooth proper surfaces. And then there are various criterions for these, like a fun one for this talk that will appear later is that if you're a smooth cubic, I got this out of Kolar's book, if you're a smooth cubic surface with two skew lines, either over K or over a quadratic extension, you're K-rational. Smooth cubic surface with two skew lines defined over some rational extent, some degree 2 extension, two skew lines defined over some K adjoint square root of D, let's say, not in characteristic 2. Okay. Let's make some Gromov Witten invariants.
Can I ask you, maybe this, I think the question was already asked, but I didn't get the answer. So what does it mean to evaluate the Sheaf GW on pi naught of x?
Let's take the set of pre-Sheaf maps from pi naught of x to GW.
Okay, so it's like GW not underlined.
Well, it's got to have an underline so that we have a notion of GW as a pre-Sheaf. I mean, it's a sheaf. Sorry, I mean, the maps of pre-sheaves are the same as maps of sheaves. So you could also say, let's view it as maps of sheaves from those two sheaves. So we've got two sheaves of sets, and we're taking, you know, the maps that you know, the natural transformations between them. That is a set. It's endowed with a group structure.
X is a sheaf
on smooth K.
It is an object in the homotopy category, but I can view it as a sheaf of sets.
Yes, please.
Okay, just because you don't represent it by a sheaf of sets.
Yes.
In this, okay.
So we should think exactly that, you know, GW is this discrete invariant, so it's going to factor through pi naught. So since it's A1 invariant and a sheaf of sets, so a rational curve, let's start with a rational plane curve. Rational means genus 0 in this context. Let's talk about curves in P2. So a degree D rational plane curve over C is a map P1 to P2 given by 3 homogeneous degree D polynomials. There are D plus 1 interesting coefficients of a polynomial, so that gives us 3D plus 3 P1 itself, though, has 3 dimensions of automorphisms, and P2 has 1 dimension that you divide out by to make all points the same. So we've got 3D minus 1 interesting dimensions. So there should be finitely many degree D rational curves through generally chosen 3D minus 1 points. Over C, this is independent of the generally chosen points. There are finitely many. Let's say that ND is this number of such of them, and if we want to know the number of degree 1 curves through 2 points, that's the number of lines through 2 points, it's 1. And if we want to know the number of degree 2 curves through 5 points, it's a conic through 5 points, and there's 1 of those. And then the number of cubics through 8 points. It's an old calculation that there are 12 of them. It's a 19th century result of Zeuthen, that N4 is 620 and N5 is 87,000. And then this is 19th century, and this is intersection theory, 87,304. And it is an achievement of Gromov Witten theory that that Kontsevich made a recursive formula. So there's a connection to mathematical physics and a general way for counting curves that is called Gromov Witten theory. And recursive formula. One of the things that Gromov Witten theory does is it gives us a good count even when we're not in general position. So let's let's define those counts. So let's let m bar gn denote a space of all rational maps. And let's say X is projective over C. And then let's let
So if you do it in characteristic P, do you get a map of the same, generically finite map of the same degree, but possibly, and is it a tall or not necessarily?
No, it's not. It's a tall over the. Which map are you going to say? The map that I'm about to write down, or?
When you count, take the universal family.
Yes.
And so you want to look at the scheme over 3D minus 1 genetically chosen point. So this kind of scheme theoretic thing over 0 in characteristic P. So this is, you get something which is generically finite and of the same degree.
Even in characteristic P, there's a large locus where the map is a call.
Okay, so it's the same.
It's codimension 1 though. It's not codimension 2. The complement. So let's talk about that map, which is a tall. Let's look at all rational curves. So let's make a moduli stack of them. So we'll let m bar 0n x beta, we'll choose beta in H2 of x z, and it's a space of maps from a genus 0 curve. It can have many components, but they have to be nodes to x together with n mark points. Where C is again, it can have more than one component, so it can. But you can glue components, but it has to be nodal. So C is a nodal arithmetic genus 0 curve. And U is a map from C to X, and it has finite automorphisms, so it's stable. And then a P1 through Pn are marked points of C in the smooth locus. This can have components of many different dimensions. That there is a virtual fundamental class of a dimension, the canonical class of X. So this is the C1 of Tx is minus our class of omega of X, tangent space, cotangent space, and the integrated over B minus 1. So this gives a 3D in the case of X is equal to P2. And we have an evaluation map which takes the map U and it evaluates it at the ith point. So the ith evaluation map from 0n xb to x takes U C x with all these points and takes it to U of pi. And the Gromov Witten invariant counting.
Definition related to B, right?
It's in class, I'm sorry.
Yeah, but there's no definition.
Thanks a lot. So we need to fix its degree. So then we can make an invariant counting curves passing through duals of cohomology classes in X. So we can make a Gromov Witten invariant and 0 xb a1 through an as a push forward or an integral over this stack of stable maps of the pullback of these cohomology classes cupped together. So for example, if AI are Poincare dual to a point, equals Poincare dual of a point, these are the curves passing through the points, and we have that n0xb point is a virtual degree of the evaluation map on all the points. Okay, so this talk is about what happens over other fields like Q and FP, and
so in this case, is it true that the other components involving stable curves which are not A1 in this space, in this example of the greedy rational plane curves, if they do not contribute to the counting?
You can contribute some of them to the counting. I don't know what their local index is. So let's get there. It's true that when we make an entirely enumerative elementary statement, that we're only going to be able to have this nice geometric interpretation over the étal locus. But in theory, there is some other. Why don't we get there? You can absolutely define a local index for other things where it's not étal, and you can add them up, and it's a degree.
But those numbers, are they the Gromov Witten? By asking, those are the Gromov Witten numbers, or?
So we're going to get something whose, I'm not quite sure I understand your question. There are a lot of Gromov Witten invariants. We get to pull back cohomology classes and then push them forward. And we can push forward in some sort of oriented theory. So like we'll have push forward, as opposed to being oriented in the sense of Charanya's talk, but if you're oriented with an SL orientation, then we have push forwards like an integral for those theories, like Hermitian K-theory. And
maybe the question was, how do you get these numbers, or how do you get these n sub?
Oh yeah, so, right. So this would be n0 p2 d times p1 point.
So you have to know that only the smooth curves, the map from P1 to X, the actual maps contribute. So in principle, the most moduli spaces have other stuff.
That's true.
You have to know that the virtual fundamental class doesn't see the other stuff.
So we're going to be working with del Pezzos, and we're going to be working with del Pezzos so that you have that. So P2. So you're right, but one of the things about the geometry of P2 and is that virtual count has a very elementary description for a general choice of points.
So is it because the other components are of lower, the other things are of lower dimension, or because of other reasons?
There's a lot of geometry on that M bar. In characteristic P, there's this new paper of Sho Tanimoto. Why don't we discuss this afterwards? Like there are papers coming out in 2023 saying all of your components are no bigger than of expected dimension. That's a complicated question, but I mean. There is this big locus over which it's étal, and only the real, as in the maps count. And the stuff that you ignore in the moduli space can be shown to be codimension 2 in the moduli space.
Okay, this is the answer. Okay.
Sorry, it's not codimension 2. It's image is codimension 2. We need to get rid of something codimension in the base. What I was saying is absolutely true. The moduli stack is going to have potentially very cool, interesting, hard geometry. And what you can show is that in characteristic 0, the images complement codimension 2. In characteristic P, there's a more hairy argument and so we'll get the degree that extends over all of.
In characteristic P, it's still a positive codimension.
It's still a positive codimension. Let's get there as a team. So that this, let's see, what happens for K equal to Q, QP, FP, etc. And the first thing is that the K equals R case has a lot of lovely math associated to it. So invariance of number fails. It's not the count of curves can depend on your choice. Generally chosen points. There can be 8, 10, or 12 degree 3 curves through 8 real points. But Welschinger and the open Gromov Witten invariants give an invariant signed count where you count everything with a plus or minus 1. So we can define WST XB to be, X is now over R, to be the number of degree beta rational curves passing through S real and T pairs of complex conjugate points. Complex conjugate points. And these were computed recursively in Jake Solomon's thesis. Let's put some up so that we know in a second why when we write down all of our Gromov Witten invariants, the indices are what they are. So for x equals P2, S plus 2t equals 3d minus 1. So we're running through the same number of total points. The 2 points still determine a line, and there's only one of them. Same with conics. And for degree 3, we get 8 minus, or the number of real points, or 8 minus the number of complex conjugate pairs. So now we can give, let's say, the main theorem of the talk due to Kass and Levine and Solomon, which is that under the assumptions that are written there, for instance, for any degree 4 and greater del Pezzo surface, and for basically any cubic surface, as long as you're not in degree 6, there is a well-defined degree. Degree of the evaluation map from the algebraic version. In GW of Sn, which when Sn is connected, or is in GW of K. This gives a count as though we were making them run through just K points. So as if all of these S's were 3D minus 1 with no T. So let's get all the S's and all the T's. So more generally, let some list of field extensions that are going to be our points be a list of field extensions that will be the residue fields of the points we're running our curves through. Field extensions. And they have to be a correct number of them. So the sum of their dimensions over K has to be this the same dimension of the moduli space. And let's call this sigma. Then we can twist this map by letting the Galois group act on this moduli space, which was defined over K, but also permute the points the way it would permute all the embeddings of the product of LIs into an algebraic closure. So we have a twist. Of the evaluation map to now have target, which is a product of V restrictions of S. So twist the evaluation map by sigma, and it goes from something, we'll just call it this twisted moduli space. When you take the Galois action, which permutes the copies of Sn, and twist by that, you get what's called the V restriction, whose so this is a K scheme that whose K points look like the L points of S. So think you view CP1 as an R scheme, and you stick it in there. So you can now choose Li points by choosing K points of this restriction of scalars. So the theorem says we have a well-defined degree in here, which is in GW of K when S is A1 connected. So the restriction of scalars is A1 connected if S is. For example, we can have some fun numbers in brackets. So here is an A1 connected cubic surface. So x squared y plus y squared z. And it follows from our examples that this is indeed A1 connected, except we've got to exclude characteristic 5 because it's not smooth. So then our Gromov Witten invariant n S naught in the canonical class, the minus canonical class, so it's effective, is a bracket with a 5 in it, plus a bracket with a 1 in it, plus 4 times this hyperbolic form, plus the sum of trace forms of all the fields that you're running, of the fields of definition of the points that your curve is passing through. So there's some more fun numbers contained in these trace forms. For example, so e.g., if you just have if you adjoin the square root of some gamma, your trace form is rank 2, and you get 2 plus 2 gamma. So I wanted to give a consequence of the fact that the degree is a sum of local degrees. So we've seen that the degree of f is a sum over the curves in a fiber of some local degree. And so this has the following enumerative consequence. When you know enough geometry about the moduli stack to know that there's a large open over which the evaluation map is étal. So what is the local degree of a curve? The curve in general will have singularities. So let's take, if we call this the degree of f at at U. So U, C to S, it has to be a singular curve, except in certain, except in a couple cases, because we know the genus of what a smooth curve would be, and so you have to have that many nodes. So a node of a curve has two tangent directions at it, so this is a node. And the tangent directions determine a field extension of degree 2. Maybe it's the same field extension of that your curve is defined over. So let's say this curve is defined over K of U, and the node is defined over some field extension of K of U, K of P, and the tangent directions is the field that you get by adjoining the square root of something. Let's call that something, whatever that may be, the mass of the node. And so what we get is that, so for example, for P2, so an enumerative version is for generally chosen P1 through Pj with field of definition Li with so fixed sigma equals L1 through Lj, generically chosen points with this with the residue field of Pi Li, then we have an equality that this invariant and P2, right, we can do it for S, and S beta sigma is the sum over the curves, genus 0 rational curves, rational degree D, curves U through the points of a piece recording the field of definition of the curve, and a piece recording how the tangent lines at the nodes are coming in. So the product over P node of U of C of the mass of P. So this is like a norm from K of P down to K of U. We want this in the GW of U. So since if you view this as nodes over the algebraic closure and you're taking this product, it is naturally in K of U. But if you took the nodes in the sense of the node is a single point, you want to take the norm map from K of P to K of U of this M, and you stick it in brackets. I'd like to stop there. Thank you very much.
Questions? I have a really basic question, I guess. Is there a way to see why you need this codimension to be greater than or equal to 2 for this degree?
Yeah. If in general, if you take out a piece of codimension at least 2, you don't disconnect. So if you're expecting some sort of integer degree, then if you're doing something codimension 2, you have to pick up the right integer. Thanks.
So this blackboard was not explained, this one, this.
The one up here. Yeah, except sort of by you, and I appreciate it. So we needed some geometry that didn't get explained, And we need to understand enough about M bar to find a bad piece to cut out that maps to codimension 2. Well, I guess a cop-out way is to say the geometry has to do with that. And then, as you say, if you want an elementary consequence, you have to know that there is an open subset of s to the n, or of your restriction of scalars, such that above it, your ev is atal. And it's a very classical fact that ev is atal whenever your curve is unramified. It's because if your curve is unramified, you have sections of, that when you, I don't know if you want to know, your tangent space to the moduli space can be viewed as sections of your normal sheaf, because that's how you move off of a curve. And so if your curve itself doesn't have its derivative vanishing, you compute that gives you that your normal bundle is a line bundle. It has enough sections to show that ev is unramified. Ev is unramified when the curve is unramified, or ev is atal, in fact, when the curve u is unramified. So if you have...
Using the nodes, this works also for nodal curves.
Well, right, so what do you mean for the curve to be unramified at a node? I was thinking just in the big component m, not in m bar, but you can show that on this balanced locus of, if you have two components, that m bar is smooth and ev is unramified. But I meant on m. And that's where if ds is equal to 2 in the case the lower degree del Pezzos get harder, you can see this assumption that you can just ignore if you don't care about ds equals 2. But in positive characteristic in ds equals 2, we have to have a lot of unramified maps, and that's a first glimpse of why you would want unramified maps in m bar.
M0 n is the same M0 n bar. Why?
Yeah, so this is the birational. The M Burr is the ones who have irreducible domain curve and which are birational onto their image. So it's not like a D to 1 map. And we want every irreducible component in the birational maps to have an unramified map, and this gives you a large enough locus. And you can prove that holds for other Ds. Anyway, I very much appreciate the question. There was certainly a lot that we didn't justify.
Any other questions?
Yes. So then you integrate the first transpose of the fix, and then you have the -1. What is the source of -1?
It's the dimension. It's the souped up version of the dimension count we gave with the polynomials have d plus 1, and degree d polynomials is d plus 1. But I mean, you can actually do it by computing the normal sheaf so you map, you've got this u from C to X, and that makes you pull back the tangent space of X to C, and you have a sequence from the tangent space of C to this tangent space of X to this normal sheaf, and that dimension, the normal sheaf, you can figure out from the fact that the tangent space of a sub to the tangent space of something bigger. It determines the dimension of that tangent space, which gives you the dimension of the moduli space, assuming you believe me that it was smooth, and that's an older understanding.
You're considering genus just 0.
Just genus 0 right now.
Genus 1 or Gromov Witten.
It's harder. No.
Any other questions?
I keep forgetting. So is there an analog of these recursion formulas?
That's a great question. We are thinking about it. There's a wall crossing formula for exchanging two rational points to a pair of conjugate ones, and That's the work with Erwan Brugallé that I mentioned, and Andreas Jaramillo Puentes has another point of view for toric del Pezzos.
No more questions? No, let's thank you.